Hello, my name is Jeffrey Morris. I'm a senior software engineer at Couchbase, and today I'm going to present a tale of timeouts and latency, response time observability explained. The agenda. So first we're going to talk about distributed systems and latency. We're going to talk about tracing 101, response time observability defined, a demonstration, and then what to look forward to in the SDK. Distributed systems and latency. Single computer systems represent the idealized computer model. Applications act in a fairly predictable manner. Buggy software doesn't indicate the computer itself has a problem. Assuming a hardware is working correctly, given the input, the output is deterministic. If the hardware is not functioning properly, then we can expect total system failure. Generally, the system is either 100% functional or 100% broken. There is no in-between state or partial result. The fundamentals of computer design prescribe always correct computing. If something is wrong, we expect a crash or an invalid result being returned, which is difficult to understand. Distributed computer systems are different, though. No longer the ideal computer system model, we must confront the physical world. Partial failures are expected. Failures may be non-deterministic in nature. Detecting where a failure occurs can be difficult. Applications must be resilient and be able to handle failures. Unless you're working on a local host machine with the server and database on that machine, virtually every client-server architecture can be considered a distributed system. But what could possibly go wrong? Well, if it can go wrong, it will go wrong. Cords are unplugged, we have faulty hardware, invalid configurations, server or process crashes, garbage collection pauses, network congestion, switch failures, TCP resets, unexpectedly high traffic, etc. Any number of things can go wrong. The net effect is almost always latency. For example, a client makes a request to the server. The server happens to be backed up because there's a lot of requests that day or at that time. The result is latency and a frustrated user. This invariably will manifest itself as a request timeout or the dreaded exception, timeout exception. Tracing 101. Well, the question is, how do we determine where the latency occurred? Was it on the application? Or was it on the network? Or was it on the database server? Well, the answer is through tracing. Tracing will give us the answer to where the latency was and help us identify what the issue is so we can resolve it. So what is tracing? Tracing is special accounting that records an operation's execution across its lifespan and writes it to log. Tracing breaks an operation's path into degree it spans. Request encoding on the client, dispatch to server, just decoding the response from the server, etc. Each span is timed independently and includes contextual information. A single request typically is made up of multiple spans. So let's visualize a tracing message. So a trace is a collection of spans. Every trace has exactly one root span and 0 or more child spans. In this example, we have the root span, and we also have 3 child spans. We have request encoding time, server time, which includes network time, and response decoding time. The sum of these 3 gives us the total duration, which is the latency it took for that operation to complete. So what is captured? In theory, virtually any tag or attribute can be captured. In Couchbase, we capture some pretty specific stuff. We want the operation name, the operation ID, the local address, the remote address, the latency, etc. This information is collected from the spans and gives us response time observability, or RTO. Response time observability. As of Couchbase Server 5.5, there's out-of-box support for developers to observe response times relative to a tunable threshold. The server logs and the SDK logs can be correlated. Every nth interval, any operations that have exceeded the threshold are summarized and the report logged. These reports can be visualized. The threshold logger is the lowest representation of RTO within the SDK. It's represented via a threshold logging tracer or similar object. It helps identify operations that exceed a given threshold that has been configured. It receives completed spans and verifies that the threshold was exceeded. Operations that exceed a given threshold are periodically logged with a total count and sampled the slowest one per service. Operation summaries are logged at the info level. All Couchbase SDKs come with an idiomatic implementation that's enabled by default. So here's an example of a threshold logger JSON message. Importantly, we have the service, which is KV, for key value for the memcache protocol. Our threshold, or our total number of messages that we want to log is 3. So we're going to log the three slowest operations. The operation name is get, the last operation ID, OX33. We have the local address, the remote address, we have the local ID. Then we have the total time spent. In this case, about 49 milliseconds. We also have the encoding time. So this is what the client spent, plus the dispatch time, which is very fast. So this includes server time. Threshold configuration logging is done within the SDK in the cluster options object. There's several different configurations or properties that you can configure. First, there's the interval, which is the execution that the processes are, the interval between executions that the process collects spans. We default to 1,000 milliseconds. There's the sample size, so that's the number of samples to collect per service. So we had 3 in the last example. The default is 10. Then we have a bunch of thresholds. These thresholds are where we will log a span. So, for example, KV, we will span, if a operation takes longer than 500 milliseconds by default, we will log it. Views, we give you 1 second, and then we will log it. This is configurable. For example, in the last example, I set the threshold to 0 because I wanted everything to be logged. I'll also do the same in my demonstration. So now it's time for the demonstration. So what we have here is a very basic web application. It's an ASP.NET web application, but it could be any web application. So in the startup class, this is where the process actually starts. I've configured Couchbase to be injected, and importantly, I enabled logging and the threshold tracing logger. I set the KB threshold to 0 so that any operations are captured and logged. Now I add a couple of buckets, and that's that. If I run this, application, first I'll see the console. And then I'll see the web page pop up. I'll see that I'm using the travel sample, and I've got a list of airlines. I swap back to, this is the console application. I'm logging a console, so we will see the logs written here. Now I'm going to click on airlines. So this is going to load the airlines controller. And then I'm going to select an airline. So today, let's do Air Florida. When I do that, We will get detail about the airline. There's Air Florida, well, the country it's from, United States, the ICAO, the IATA, the call sign. And then at the bottom, there's a little link here. So we're going to drill down to that in just a second. Before we do that, I want to look at the log. So as expected, I have a report. Now this report is giving me the top 2 slowest operations within that interval. Since I set the threshold to 0, it's the only 2 that occurred when I clicked that link. In that case, it was a get operation and an upsert operation. And if I look through this, I will see the get operation with its last operation ID, last local address, last remote address, last local ID. Finally, I'll see the total time spent. In this case, it seems fairly slow, but it's because I'm starting in debug mode, and the just-in-time compiler takes a bit of time to get going and warmed up. Now, if I jump back, there's also an upsert here. And you can see this is going to be a little faster, and that's because we've been through this method. It's a little faster there, 10 milliseconds. So if I jump back to the web application and I click on this link, I'm going to see a trace viewer, or I'm going to see a visualization of the tracing that occurred on this page. So this is a trace viewer that we wrote internally. It's just a little lightweight one. It's not something you'd want to use in production. It's if you're in production, you'd probably want to use something more powerful like Jaeger, but it does the job for this demonstration. So the first thing we see is a very top level span. For this case, it starts at the actual HTTP request end. Now this is the root span. Now if we go a little deeper, we see the next span is the airline controller.get. So this is the get controller, or this is the airline controller that we called when we clicked the link for Florida Airlines, or Air Florida, excuse me. So the time, so you see the start, you see the duration, the dispatch, the encoding. Now if you go down, you see a connection, initialized connection. So what's going on here is we've lazy loaded the SDK. So when we do that and we click on it, it's going to load all the connections to the Couchbase server and then initialize them and run through the negotiation process. Hello is going to be called, and they'll give you the request encoding and the dispatch to server time. We're going to get an error map, our authentication. We'll run through authentication, and then we're going to load another connection. So we're going to load a couple connections and some authentication. Finally, we're going to call select bucket. Select bucket again. And I'm gonna go down a ways because this just goes over and over again as we load all our connections, and all our connections are warmed up. Now, if I go down a ways, I get to a get method. Now, this is a memcache get method that corresponds to what we saw in the report. You see the duration. Like I said, it was a fairly long one. So it's almost at 700 microseconds. And we see the encode time, the last dispatch time, and these are broken into spans themselves. And then finally, we see a query. So we actually internally, in that controller method, we did a couple of operations. We did a get method request, we did a query request for a nickel query, and we also did an upsert. So here's the query, the nickel query. Now this wasn't captured in the report because I limited it only to KB. And here's the upsert. And like I said, if I jump back to my report, we will see the get and the upsert captured here. So that concludes our demo. So looking forward, well, first we got to look back a little bit. So SDK 2 was based on Open Tracing, which is a vendor agnostic tracing API, cloud native and computing project. All of the SDKs supported open tracing for SDK2. That being said, things have changed. There's been some evolution. Open tracing plus open census, another tracing API, have joined. And now we have open telemetry. So what direction is the SDK is going to go? We're going to move to open telemetry. It's going to happen. It's going to take a little time. I think currently SDK3, most of the applications support open tracing only, but they will eventually support open telemetry, and that's the API that we're going to default to. .NET's there's a caveat because it has a built-in activity API that actually is basically what OpenTelemetry exposes. We'll be reviewing and concentrating on what is collected in the storage format over what tracing API to use. We think that's more important. Additionally, we're in the process of writing a new RFC to address consistency across all SDKs with respect to tracing. Thank you.